Now we come to chapter 9 module 2. In this module we shall find out Hankel transform of some functions and also we shall apply Hankel transform to solve boundary value problems. In example 1 we shall find Hankel transform of order 0 for the function fr equal to e to the power minus ar by r, where a is some positive constant. Now, Hankel transform of order 0 of the function e to the power minus ar by r as per definition is equal to integral from 0 to infinity e to the power minus ar by r into r j0 rho r dr. This is equal to integral from 0 to infinity j0 rho r e to the power minus ar dr. Now, here to evaluate this integral we shall use the series expansion for j0 rho r, which is given by summation n equal to 0 to infinity minus 1 to the power n rho r by 2 to the power twice n divided by n factorial whole square. Using the series expansion for j0 rho r, the Hankel transform of order 0 of e to the power minus ar by r is equal to summation n equal to 0 to infinity integral 0 to infinity minus 1 to the power n rho r by 2 to the power twice n divided by n factorial whole square e to the power minus ar dr. This is equal to summation n equal to 0 to infinity minus 1 to the power n rho by 2 to the power twice n by n factorial square into integral from 0 to infinity e to the power minus ar r to the power twice n dr. Writing ar equal to t, this integral is transformed to 0 to infinity e to the power minus t to the power twice n dt preceded by the summation, this portion. Now, this integral can be written in terms of gamma function, that is gamma 2 n plus 1. So, that Hankel transform of e to the power minus ar by r is equal to summation minus 1 to the power n rho to the power twice n gamma twice n plus 1 divided by 2 to the power twice n factorial whole square a to the power twice n plus 1. And this is equal to 1 by a summation n equal to 0 to infinity minus 1 to the power n twice n factorial by 2 to the power twice n into n factorial square rho square by a square to the power n. Now, the expansion for 1 plus x to the power minus half is given by summation here on the right hand side, where this symbol is written in this form. Symbol has this meaning as minus 1 to the power n twice n factorial divided by 2 to the power 2n into n factorial square, and this summation is valid for mod x less than 1. Now, looking at this summation and comparing with this summation, we can write Hankel transform of e to the power minus ar by r as 1 by a into 1 plus rho square by a square to the power minus half, which is equal to 1 by root over rho square plus a square, where a is positive. Now, making a tending to 0 plus Hankel transform of 1 by r is equal to then integral from 0 to infinity 1 by r into r j naught rho r dr, and which is equal to integral from 0 to infinity j naught rho r dr, which is equal to 1 by rho for rho positive. Next we come to Example 2. Here we have to find Hankel transform of order 0 for the function fr equal to e to the power minus ar square, where a is some positive constant. Now, Hankel transform of order 0 is denoted by capital F naught rho, that is according to the definition is integral from 0 to infinity e to the power minus ar square r j naught rho r dr. This integral also we shall evaluate by using the series expansion for the Bessel function of order 0 j naught rho r, which is given here. Now, we substitute this series expansion in this integral to obtain f naught rho as this. Here the integral can be simplified by substituting r square equal to t, so that f naught rho is given by this expression, and the integral here, that is the t integral, can be simplified to write it in terms of gamma function, that is this t integral is equal to gamma n plus 1 by a to the power n plus 1, and that is equal to n factorial by a to the power n plus 1. Thus, with this simplification, f naught rho is equal to half summation n equal to 0 to infinity minus 1 to the power n rho to the power twice n divided by 2 to the power twice n factorial a to the power n plus 1, and that can be simplified to obtain 1 by twice a e to the power minus rho square by 4a. So, we have obtained the Hankel transform of the function ar, that is fr, that is equal to e to the power minus ar square. This can also be evaluated by using the integral representation of Bessel function given by j0z equal to 1 by 2 pi integral 0 to 2 pi e to the power I z cos theta minus phi d theta in two dimensional Fourier transform of small f x y equal to e to the power minus a x square plus y square, where x is r cos theta and y is r sin theta, r lying in the interval 0 to infinity and theta in the interval 0 to 2 pi. And this is given by capital FKL, which is the two dimensional Fourier transform of the function e to the power minus a x square plus y square, which is equal to 1 by 2 pi double integral from minus infinity to plus infinity e to the power minus a x square plus y square e to the power I k x plus L y dx dy as given by equation 1. The right hand side of 1 can be evaluated in two ways. The first method is 1 by 2 pi integral from minus infinity to plus infinity e to the power minus a x square plus I k x dx into integral from minus infinity to plus infinity e to the power minus a y square e to the power I L y dy. That is, we have separated out x integral and y integral. Next, some adjustment is made so that power of e is minus a x plus I k by 2a whole square plus k square by 4a square, and also in the y integral the power of e is e to the power minus a y plus I k by 2 whole square plus L square by 4a square dy. Now, taking out this term e to the power k square by 4a square and e to the power L square by 4a square, we are left with integral from minus infinity to plus infinity e to the power minus a u square du, where we have substituted u for x plus I k by twice a, and here in the second integral, that is v integral, we have substituted v for y plus I k by twice a, and this can be evaluated, these two integrals can be evaluated in terms of gamma function. So, that we obtain 1 by twice pi e to the power minus k square plus L square by 4a root over pi by root a into root over pi by root a, and that is equal to 1 by 2a e to the power minus rho square by 4a as given by equation 2, where rho square is k square plus L square and k is rho cos phi, L is rho sin phi. The second method is that right hand side of 1 can be written after putting xy as r cos theta and r sin theta and kl as rho cos phi and rho sin phi. We get right hand side of 1 as 1 by twice pi integral from 0 to infinity integral from 0 to 2 pi r e to the power minus a r square e to the power I r rho cos theta minus phi dr d theta. And this is written as integral from 0 to infinity r e to the power minus a r square 1 by 2 pi integral from 0 to 2 pi e to the power I r rho cos theta minus phi d theta dr. Now, we have learnt in module 1 that the inner integral is j naught rho r. So, that this is equal to integral from 0 to infinity r e to the power minus a r square j naught rho r dr, which is the Hankel transform of the function e to the power minus a r square, and that is equal to capital F naught rho. Thus, we have found out Hankel transform of e to the power minus a r square as 1 by twice a e to the power minus rho square by 4a. Here we may note here that if we put twice a equal to 1, then Hankel transform of e to the power minus r square by 2 is e to the power minus rho square by 2. So, we can see that the function e to the power minus r square by 2 is self reciprocal under Hankel transform of order 0. And it is interesting to note that the function e to the power minus x square by 2 is self reciprocal under Fourier transform, and this was shown in chapter 6 where we have done Fourier transform. So far we have found out Hankel transform of order 0 of some function. We shall consider few more examples. Next we come to example 3. Here we shall find out Hankel transform of order 0 of the function e to the power minus a r, where a is positive. We write Hankel transform of order 0 of e to the power minus a r as integral from 0 to infinity e to the power minus a r r j 0 rho r dr. Now, we can write this integral as minus dda of integral 0 to infinity e to the power minus a r j 0 rho r dr. Now, the integral is the Hankel transform of the function e to the power minus a r by r. So, that Hankel transform of e to the power minus a r is equal to minus dda of Hankel transform of e to the power minus a r by r. And we have already obtained Hankel transform of e to the power minus a r by r in example 1, and so that we can write it as minus dda of 1 by rho square plus a square to the power half, and this is equal to a by rho square plus a square to the power 3 by 2. Next we shall find out Hankel transform of order nu of the function f r, which is equal to r to the power nu for r less than equal to a and 0 for r greater than a. in example 4. So, we write Hankel transform of order nu of the function fr as integral from 0 to a r to the power nu r j nu rho r d rho, which is equal to 1 by rho to the power nu plus 2 integral from 0 to rho a x to the power nu plus 1 j nu x dx, where we have substituted x for rho r, and this is equal to 1 by rho to the power nu plus 2 integral from 0 to rho a d dx of x to the power nu plus 1 into j nu plus 1 x. We have used the result that x to the power nu plus 1 j nu x is equal to d dx of x to the power nu plus 1 j nu plus 1 x. This is the result for Bessel function, that d dx of x to the power nu j nu x is equal to x to the power nu j nu minus 1 x. We have used this result. So, Hankel transform of order nu for the function fr is equal to 1 by rho to the power nu plus 2 into rho a to the power nu plus 1 after evaluating this integral, and that is equal to a to the power nu plus 1 by rho j nu plus 1 rho a. Next we come to example 5. Here use the Parseval relation of Hankel transform to evaluate the integral from 0 to infinity j nu plus 1 a r j nu plus 1 b r by r dr for nu greater than minus half and 0 less a less b. To show this, we write capital F nu, or rather capital F rho is equal to j nu plus 1 a rho by rho, and capital G rho we write it as j nu plus 1 b rho by rho. And from example 4, we note that capital F rho, which is the Hankel transform of small fr, where small fr is r to the power nu by a to the power nu plus 1 for r less than a and 0 otherwise, and capital G rho is the Hankel transform of small g r, where g r is r to the power nu divided by b to the power nu plus 1 for r less than b and 0 otherwise. So, we use the Parseval relation that integral from 0 to infinity rho capital F rho capital G rho d rho, this is equal to integral from 0 to infinity r small f r into small g r dr. This is the Parseval relation. We substitute here for capital F rho and capital G rho defined here to obtain integral from 0 to infinity j nu a rho plus into j nu b rho divided by rho d rho. This is equal to integral from 0 to a r to the power nu a to the power nu plus 1 as we have defined here. Both are defined to be non-zero for r less than a. So, the right hand side integral is 0 to a r to the power nu a to the power nu plus 1 into r to the power nu b to the power nu plus 1 r dr for a less than b, and that is equal to 1 by a b to the power nu plus 1 into integral 0 to a r to the power twice nu plus 1 dr, this integral can be evaluated to get 1 by 2 nu plus 1 a to the power twice nu plus 2 divided by a b to the power nu plus 1, and this is equal to 1 by twice nu plus 1 into a by b to the power nu plus 1, where 0 less a less b and nu is greater than half. So, we have proved the result. Now, we come to the application of Hankel transform. Here we shall use Hankel transform of order 0 to solve the partial differential equation r del to phi del r2 plus d phi del phi del r plus r del to phi del z square equal to 0, where r lies in the interval 0 to infinity and z positive, with the boundary condition phi at z equal to 0 is fr and r is positive, and fr is a known prescribed function, and also we have the boundary condition that phi rz tend to 0 as root over r square plus z square tend to infinity for z positive.
Got it.
For solution of this boundary value problem, we use the 0th order Hankel transform defined by capital phi rho z be the Hankel transform of small phi rz, and which is denoted by h naught phi rz and defined as integral from 0 to infinity small phi rz r j naught rho r dr. Now, if we multiply this PDE on its both sides by r j naught rho r and integrate between 0 to infinity with respect to r, we see that this PDE reduces to an ODE in capital phi, which is given as d2 capital phi dz2 minus rho square capital phi equal to 0 for z positive. And also we multiply this boundary condition on its both sides by r j naught rho r and integrate with respect to r from 0 to infinity to see that it gives capital phi at z equal to 0 is capital F rho, where capital F rho is the Hankel transform of order 0 of the function small f r. And also we see that capital phi rho z tends to 0 as z tend to infinity. Now, appropriate solution of this ODE satisfying this boundary condition is given by capital phi rho z equal to capital F rho e to the power minus rho z. So that if we take the inverse transform, we find small phi r z as integral from 0 to infinity rho capital F rho e to the power minus rho z j naught rho r d rho. So, this is the solution of the given boundary value problem with the boundary condition phi r at z equal to 0 is f r. Now, if f r has the form root over r square plus a square to the power minus half, that is f r equal to r square plus a square to the power minus half for a positive, then we know that from example 1 that capital F rho is the Hankel transform of the function small f r, and it is integral from 0 to infinity r f r j naught rho r dr, which is equal to minus a rho by rho. So, capital F rho is known then, and if we substitute capital F rho here in the expression for small phi, then we obtain small phi r z as integral 0 to infinity e to the power minus a plus z j naught rho r d rho. and that is equal to 1 by root over a plus z whole square plus rho square as seen from the example 1. Here I mentioned that this is possible because the Hankel transform of order 0 and its inverse has the similar formula. So, taking particular form of small fr, we have obtained the solution for the boundary value problem here. So, in this module we have learned how to find out Hankel transform of some function, and also we have learned how to use Hankel transform to solve boundary value problems. With this we conclude module 2 of chapter 9.